of modulation schemes in the presence of noise. And I believe we have covered the effect of noise on DSB suppressed carrier, where the result that we had at the end is that the signal to noise ratio at the output of a DSB suppressed carrier is the same as the signal to noise ratio for the baseband system. We had earlier defined the signal to noise ratio for the baseband to be given by the power of the received signal divided by N naught times W. So DSB suppressed carrier does not have any other signal to noise ratio advantage over the baseband system. Likewise, we also looked at SSB, and in the case of SSB, we had exactly the same result, which said that the signal to noise ratio for an SSB signal system is the same as the signal to noise ratio of the baseband system, where of course the signal to noise ratio of the baseband system is again given by the received power divided by N naught W. So the next modulation scheme we now want to look at is the DSB full carrier, or at times called the conventional AM. In the case of the conventional AM, our modulated signal is given by this expression for U of t, where AC is the carrier amplitude, small a here is the modulation index, and M sub n is the normalized message, or what we call the baseband signal. The message is the baseband signal. So that will be the transmitted waveform. The received waveform in the presence of noise would be simply U of t plus N of t, where N of t is narrowband noise represented by NC times cos minus NS times sine, which is the quadrature representation of narrowband noise. So U of t plus N of t can then be written as R of t, where that is now our received signal R of t. In the receiver, we demodulate the signal using a synchronous demodulator. By that, we simply mean that we take R of t, we multiply it by cos 2 pi fct again, and the result of that multiplication goes through a low-pass filter, which will extract only the low-pass components. So the output of the low-pass filter in this case would be given as 1/2 of AC into AM sub NT plus NC. Now, where essentially this here is the received signal component, and NC is the noise component. But in the case of conventional AM, we are not interested in the DC component. The DC component is the component with AC multiplied by 1/2. So the only component that we are interested in is the component that has the baseband signal, which is the component with the M sub n. So essentially then, that the received signal, the demodulated signal would be 1/2, where this 1/2 is this 1/2, and then the AC times AM which comes from this component here multiplied by 1/2 and multiplied by AC, plus the 1/2 multiplied by the NC, because notice that this bracket here is actually this bracket here. So the 1/2 is multiplying both components, the desired signal component and the noise component. So this then would be the output of the low pass filter after we have removed the DC component. So we are now interested in obtaining the signal to noise ratio at the output of the low pass filter, which is essentially, let me use a different pen, which is essentially the power of this, which is the desired signal component, divided by the power of that. Okay, that will be the signal to noise ratio at the output of the low pass filter. Now, the power of the first term is simply 1/4 AC squared, small a squared, times the power of M sub n. And then the power of the noise component would also be 1/4, because we simply square whatever multiplier we have from amplitude to power, we square it. So it will be 1/4 times the power of NC of T. So essentially, the signal to noise ratio at the output can then be written as the power of the desired signal component divided by the power of the noise component. Okay? And then with that, this 1/4 would cancel with this 1/4, and we end up with small a squared AC squared and then PMN divided by PNC. Now, if we multiply this expression by 1 plus A squared PMN in the numerator, and we also divide by 1 plus A squared PMN in the denominator, we would not have modified that expression. But in so doing, well, notice that this small AC PM is what we have. This term here is actually the same as this term here without the AC, and then the AC squared is this AC squared that we have over there, and we will have actually multiplied in this case by 1 plus A squared PMN. So rearranging that, okay, we can essentially rearrange that and say we will have the A squared PMN. Let me get a different color pen. Go back to red. So we will essentially have this component here, which would be the component that actually comes in from the small a squared PMN up divided by A squared PMN, which is this component here. And then if we look at it, this term here is actually the received signal power, and then divided by N0 W. So essentially then, the signal to noise ratio at the output can then be written as, so this term here, which is the signal to noise ratio at the output, get a pen. Which is the term that we want to evaluate. This term here can then in fact be written as that term there, right? And if we call this multiplier here some value eta, we can then say that for DSB full carrier, the signal to noise ratio at the output is given by some value eta times the signal to noise at baseband. So now we see that the DSB full carrier is different from SSB and DSB suppressed carrier. For DSB suppressed carrier and SSB, the signal-to-noise ratio at the output is exactly the same as the signal-to-noise ratio baseband. But for DSB full carrier, the signal-to-noise ratio at the output is equal to the signal-to-noise ratio at baseband multiplied by some coefficient which we have actually defined as eta in this case. Okay, right. Let's look at an example. This is a slightly complicated example. So in this example, we have a message M of t that we need to transmit. So this is our baseband signal. And we are told that the baseband signal is actually a random process which has an autocorrelation given by this. So we are not actually given actual M of t, we are given the autocorrelation of M of t. But we are also further told that the maximum value of M of t is 6. And this message M of t is, after modulation, is transmitted to a destination via a channel which has got an attenuation of 50 decibels. And there is also additive noise, and the additive noise power spectral density is given as N0 upon 2 would be equal to 10 to the minus 12. And then lastly, we are told that at the receiver, we need to achieve a signal-to-noise ratio of 50 dB. So we need to achieve a signal-to-noise ratio of 50 dB. So this is the signal-to-noise ratio at the output. So the question then says, determine the required transmit power and channel bandwidth for each of the following three schemes: DSB suppressed carrier, SSB, and DSB full carrier, or what is called conventional AM, with a modulation index of 0.8. Okay, right. So what do we know? We know the autocorrelation, and if we know the autocorrelation, which is Rm of tau, it means we can calculate the power spectral density, because we know that the power spectral density and the autocorrelation are a Fourier transform pair. So since our autocorrelation is a sinc squared, then the power spectral density, we can look it up from tables, and we'll see that it is essentially a rectangular function in frequency. And that rectangular function in frequency will have essentially values of f going from minus 10,000 to plus 10,000. And that 10,000, actually, we obtain it by essentially looking at this value here. So if this value here that I'm circling was 1, then your rectangular function pi f would essentially have frequency components going from -1 to +1. So this then essentially means that if we were to draw the power spectral density, so these are the axes, that is the y-axis, and this is the x-axis, and this x-axis is frequency, and this here is the power spectral density. Let's call it S sub m of f, which is the power spectral density. Then all we're saying is that our power spectral density is a triangular function that does this and does that. And this value here is essentially 10,000. It's given by that value there. So that's the power spectral density of the baseband signal. Now, we should then be able to then say, we know that our baseband signal-to-noise ratio is always given by the received power divided by N0W, which is going to be essentially PR, the received power, and we substitute for N0, which is this one, and we substitute for W, which is 10,000. So it means actually then our signal-to-noise ratio at baseband is 10 to the 8 PR divided by 2. But we are interested in the transmit power. We know the relationship between the transmit power and the received power. It's given in the question, because the question says that the attenuation that we have is actually 50 decibels, which means essentially the transmit power is reduced by a factor of 50 dBs. Convert that 50 dBs to an actual power ratio, not a decibel ratio, then it means essentially we're saying PT upon PR is equal to 10 to the minus 5, which gives us that PR is equal to 10 to the minus 5 times PT. We can then substitute for, hello?
For your signal to noise ratio, your W, how is it 10 to the 4? Shouldn't it be 10,000?
Oh, sorry, no. It's you mean the W?
Yes, sir, in the signal to noise ratio.
Yeah, the W is 10,000.
Okay.
Which is the 10 to the 4. So if I go back, let me get a different color pen so that there's not too much red. If I go back here, the N naught here is given as 2 times 10 to the minus 12. The W here, we have just simply said that our W would be equal to 10,000, which is essentially this number here. And that
Thank you, sir.
W essentially is that the value of the frequency at this point there. Making sense?
Yes, sir, thank you.
Okay, right. So we can write then our signal to noise ratio at baseband in terms of the transmit power by simply substituting for PR in this expression. So this PR here, if we substitute for it and simply say it's given by this term here, then we can write our signal to noise ratio at baseband as 10 to the 3 PT divided by 2. Now we can now start looking at the 3 modulation schemes. For DSB, again, this in the exam, I will actually give this actually not as DSB AM, but DSB suppressed carrier. For DSB suppressed carrier, so I'll be very explicit, that is DSB suppressed carrier, DSB full carrier, and SSB. Those are the 3 schemes we looked at. For DSB suppressed carrier, we've already derived, and this formula will be provided on your formula sheet, is that the signal to noise ratio at the output is equal to the signal to noise ratio baseband, which means that the signal to noise ratio at the output is simply going to be given by this, which is what we've derived as the signal to noise ratio baseband. But we've been told in the question that we want our signal to noise ratio at the output to be equal to 50 dBs, which means in fact 50 dBs can be converted to 10 to the plus 5. It means then that this term here is equal to 10 to the 5. Rearranging that, we can then find that our transmit power then in this case needs to be 200 watts. That will be for DSB suppressed carrier. Of course, we know that the bandwidth of a DSB suppressed carrier has essentially an upper sideband and a lower sideband. So the bandwidth is going to be 2W, and if our W is 10,000, it means then that the bandwidth will be 20,000. We can do the same for SSB. For SSB, the signal to noise ratio at the output is equal to the signal to noise ratio at baseband. We told that the signal to noise ratio at the output must be 50 dBs, and we've derived that the signal-to-noise ratio baseband is given by this term here. So doing the same, equating this to that, equating those two, we can solve for P of t, and obviously P of t will come to be exactly the same because that is what we had in the case of DSB suppressed carrier. The only difference though is that for SSB, our bandwidth is only one sideband. You either transmit the upper sideband or you transmit the lower sideband. Therefore, the bandwidth is going to be W, which is 10 kilohertz. The conventional AM is actually a bit more difficult, a bit more involved. In the case of the conventional AM or DSB full carrier, we have derived the expression which says the signal-to-noise ratio at the output is going to be some value eta times the signal-to-noise ratio baseband. Therefore, it will be equal to eta times what we have derived to be the signal-to-noise ratio baseband, which is 10 to the 3 pt upon 2. We can equate that to essentially 50 dBs, which is 10 to the 5. But in this case, we need to also find the value of eta before we can solve for pt. But eta, we have derived the expression for eta, and we have said that eta is then given by the modulation index a small a squared times pmn divided by 1 plus a squared pmn. In this question, a is given. We are told that the modulation index is 0.8, so we know that, and we would know obviously that as well. So the only term that we need to find is pmn. Now, pmn is easy because we are given the autocorrelation. Pm, the power is the autocorrelation at tau equal to 0. So Pm, we can calculate that, and it will essentially be 16. Now, the normalization, we are told that the maximum value of M is 6. So if we are normalizing it in terms of amplitude, we would simply divide the amplitude of M by 6. But if we are normalizing in power, we have to divide it by 6 squared. So therefore, our PMN is then going to be equal to PM divided by 6 squared. And knowing our PM to be 16, we can then say PMN then is 16 upon 36. Then with that, now we can find our eta. Then this comes from the modulation index. This comes from PMN. And likewise, that is from the modulation index. And this is from PMN. And that gives us an approximate eta of 0.2. So plugging in eta and equating this, which is the signal-to-noise ratio at the output of the DSB full carrier, we equate it to the required signal-to-noise ratio of 10 to the 5. We can solve for PT, and in this case, PT comes out to be about 900 watts. The, the bandwidth of a DSB full carrier is always going to be equal to 2W because we transmit both sidebands in addition to the carrier. So for the 3 modulation schemes, then we've determined what the transmit power is going to be and what the bandwidth should be. Okay, so that's the case of linear modulation, where in this case we have looked at the signal-to-noise ratio at baseband. And then we considered 3 modulation schemes, DSB suppressed carrier, where we found that the signal-to-noise ratio at the output is the same as the signal-to-noise ratio at baseband. We then looked at SSB, and we found that the signal-to-noise ratio at the output of an SSB is the same as the signal-to-noise ratio of the baseband signal. And then lastly, we looked at DSB full carrier, where we saw that the signal-to-noise ratio at the output would be equal to some factor eta times the signal to noise ratio at baseband. Okay, so those are the three concepts that you really need to know. The exact formulas would, if you forget them, those would actually be provided in a formula sheet. Right, so that then covers the performance of noise in linear modulation. What about if we're looking at nonlinear modulation, which we also call angle modulation? Nonlinear modulation, we looked at two schemes, and these were phase modulation, PM, and the next one was frequency modulation. Those are the two nonlinear schemes that we have. Or alternatively, they are called angle modulation because they involve modulating the phase of the carrier rather than the amplitude of the carrier. Now, the calculation of the signal to noise ratio at the output for frequency modulation and phase modulation is a bit complicated. The complication arises from the fact that the noise is always added to the amplitude. Okay? So the noise is added to the received signal. But the message is contained in the phase. Okay, so let me repeat that. The received signal R, oops, let me get rid of this and try and write it properly. The received signal R is actually going to be equal to whatever is transmitted, which is U plus N. Okay, so R of T is going to be U of T plus N, where N is the noise. Now, this is a linear addition of the signal, transmitted signal and noise. Okay. But the modulation is embedded in the phase of U. So the noise would only affect the message only if the noise contaminates the phase. So the question is, to what extent would this here affect the phase of the U of T? Okay. So that's really the issue with phase modulation and frequency modulation. Looking at it again in terms of actually the equation, our U of T is given by this general expression where the phi of T is obtained through an integral in the case of frequency modulation, and in the case of phase modulation, the phase phi is directly proportional to M of T. Now, so the effect of noise, which is this N of T, which can be written using its narrowband representation. To estimate the effect of noise, we actually have to see the extent to which this term N of T actually affects the phase term. Okay? The phase term is either this component here for frequency modulation, or it's actually this component for phase modulation. So essentially the system that we actually have is we have a received signal here, which is simply U of T plus narrowband signal. And the narrowband arises from the fact that we actually have a bandpass filter. Okay. We have to have a bandpass filter because our U of T is a band limited signal. And then we go into an angle demodulator, and then we go into a low pass filter. So what we want to do is to find the signal to noise ratio at the output there. The calculation is a bit complicated. What complicates it is the effect of noise. When you actually take this noise and you go into an angle demodulator. Okay. Now, so I've skipped the derivation of the noise power spectral density, but what we actually end up with, and again, this formula would be given in your formula sheet. What we'll end up with is that the power spectral density of the noise at the output for phase modulation will also still be flat. It will be a flat power spectral density. The only difference is that instead of being n naught upon 2, it will n naught upon AC squared, where AC is the carrier frequency, sorry, the carrier amplitude. The case for frequency modulation, the power spectral density of the noise at the output has a parabolic shape. Yeah. So it's no longer flat. So that means then that using these two, we can essentially find the noise at the output by simply integrating this between minus W and plus W in the case of phase modulation. And in the case of frequency modulation, we would integrate between this point and that point, where this curve here is essentially a parabolic curve. And in this case, for phase modulation, this is simply a flat expression. Now, with that, we can calculate our P, our noise power, and what we will find then is that the noise power in the case of frequency modulation would be given by 2n naught W cubed upon 3AC, and in the case of phase modulation, it will be given by slightly simpler expression. Now, obtaining then the signal to noise ratio at the output as the power of the desired signal component divided by the power of the noise, we end up with this expression for frequency modulation, which again is going to be given on your formula sheet, and we end up with this expression for the signal to noise ratio for phase modulation. This formula can be written in a variety of ways by using the relationship between the modulation index B and the maximum value of M, and also the fact that the received power, the PR, is always going to be AC squared upon 2 for an FM and an phase modulation scheme. So the other manifestations of this formula are that you can actually write it in this form for frequency modulation, or you can also write it in this form by essentially doing a number of different substitutions. And for phase modulation, what we would find then is that the expressions would either be this second expression or this second expression. Those are all equivalent expressions. You can also find the formula written in terms of by eliminating the beta and write it in terms of the bandwidth expansion factor, where the bandwidth expansion factor omega is equal to 2 into beta plus 1. This comes from the Carson's rule, remember, for the bandwidth. And then in that case, then, if we write omega as 2 into beta plus 1, we can correspondingly write the same expression for the signal to noise ratio for FM in that form, and then the signal to noise ratio for PM in this form. Now notice that this is really not that different from what we saw for DSB full carrier. For DSB full carrier, we saw that the signal to noise ratio at the output is equal to the signal to noise ratio baseband multiplied by some value which we called eta. So the only thing is the eta that we had for DSB full carrier is different from the eta that you have for FM, and also different from the eta that you have for phase modulation. But the general form of the two expressions are the same. Okay, right. Let's look at just one example. The example says, determine the required received power. So in this case, they're not asking for a transmit power, but the received power. Determine the received power, and they specifically want it for an FM system with a modulation index of 5, so beta F is given, and the bandwidth of the message is 15 kilohertz. So essentially, we are given the value of capital W, and the power spectral density N naught is given as 10 to the minus 14. So we actually have N naught. And then the power of the normalized message, so we are given PMN of the normalized message is 0.1. So it's this. And the required signal to noise ratio is 60 dBs. Okay. So essentially, we use the formula that the signal to noise ratio at the output, which we've been told that it must be equal to 60 dBs. Our formula tells us that signal to noise ratio at the output is actually given by 3 times Pm sub n, where this is the power of the normalized waveform, which we are given as 0.1, times beta squared, which we are given as 5 squared, times the SNR at baseband. Okay. Now, so we essentially know this. We know the beta. Okay, so the only thing that we need to actually do is to actually express our signal to noise ratio at baseband, but the signal to noise ratio at baseband is always going to be given by the received power divided by N naught W. Okay, so now we have a relationship between the signal to noise ratio at the output, which we know, which is essentially 60 dBs, which is 10 to the 6. We know PMN is given, we know beta is given, we know W is given. So if we look at this expression here, the PMN is known, the beta is known, the N naught is now known, the W is known, and the left-hand side is known. On the right-hand side, the only unknown is the received power PR. So substituting everything that we know, 10 to the 6 on the left-hand side, which is the signal to noise ratio at the output, substituting in all the other variables that we know, we can calculate that the received power is essentially 20 milliwatts. So it's exactly the same as the case for the DSB full carrier. The question might have actually said, so essentially in this question, what it simply says, it's simply saying this actually is your receiver. And it's saying at the signal to noise, you have essentially a signal to noise ratio here at the output. And it's given as 60 dBs. So it says calculate the received power here, PR, which is what we've actually done. But the question might actually have said, calculate the transmit power. You might have actually been told that you actually have a transmitter, which is, say, somewhere out here, with output a transmit power PT, and there is a channel gain between those. I'm going to call it L. There's a channel gain, which is L attenuation. The question might have been, find PT. It would still have been straightforward. You still obtain PR, and then once you know PR, you can then essentially then use the fact that your PR divided by PT is equal to L. PR divided by PT would be equal to L. Now, if L is given in dBs, you obviously would have to convert your L to a power ratio. So let's say, for instance, if L was an attenuation of 20 dBs, then L means it's 10 to the minus 2. Because 20 dBs, when you convert it to an actual power ratio, is 10 to the minus 2. 30 dBs is 10 to the minus 3. 40 dBs is 10 to the minus 4, etc., etc. So knowing your PR, you then be able to actually, and knowing your L, you'll be able to get your PT. Are there any questions?
Hi there, sir.
Hi.
I just have like maybe more of a conceptual question. I remember that the reason that FM, or rather angle modulation, is utilized is due to its greater noise immunity. But here it seems that it's quite similar to a DSP full carrier. So I'm just like a bit confused as to where the noise immunity would then come from.
Right. Okay. Now, when we implement FM, we actually implement it with something. I didn't cover that this year. I covered it last year with what we call a pre-emphasis. Okay, let me go back to this. Okay. The problem with FM is that if you actually look at the power spectral density, the power spectral density is actually parabolic, which means, in fact, the noise power increases essentially as your frequency increases. And if you do it this way, then you'll end up actually with a high noise. So in practice, what we actually do is we take the signal, when we transmit it at the output of the transmitter, we pass it through a filter which has got a response which is inverse to this. Right? And then we ensure that at the receiver, we essentially then do the inverse. And what you find is that by actually doing that, you actually reduce the noise, or you end up with a noise that actually is also flat. Because essentially, you would have actually done the inverse at the receiver. You actually, sorry, this is what you do at the receiver. Let me get a different pen. This is what you do at the receiver. And if you do this at the receiver to a noise that actually has a power spectral density like that, then you end up actually with also a flat power spectral density. But doing this at the receiver means you are actually distorting the received signal power, which means you actually need to do this at the transmitter before noise. So the noise will have a power spectral density of this, and then you actually use what is called a de-emphasis filter, which is that, so that you end up with a power spectral density that looks like that. But the signal simply experiences this. And what you find is that by actually doing that, you can actually reduce the effect of noise. Am I sort of making sense?
I think so. So then the effect of noise is, yeah.
Yeah, that in reality, if you look at the last portion of the textbook, that in reality, what you actually find is that when we implement an angle modulation, we actually do what we call pre-emphasis at the transmitter and de-emphasis at the receiver in order to combat the effect of actually the parabolic power spectral density. And when you do that, you end up actually with a reduced noise, signal to noise ratio. But I didn't want to go into the theory of pre-emphasis and de-emphasis this year.
Okay, so then for our purposes, like the angle modulation and the DSP full carrier would provide a similar like noise immunity.
Well, no, not similar, because it really depends on the parameters that you've got. Because
Sure.
the eta that you have in the case of AM really depends on the modulation index, and it depends on the normalized power. Now, the eta that you have in the case of FM depends essentially on, if I use the expressions that we actually have here, it depends on the beta that you actually have. It depends on the maximum value of M that you actually have. It depends on the PR that you actually have. Well, sorry, the PM, because the PR is part of the signal to noise ratio baseband. So the actual ratio really depends on the parameters that you've got. Further questions? But the point I wanted to make is, if we do not have pre-emphasis and de-emphasis, you can essentially treat, from a conceptual point of view, what you have for FM and PM in a similar manner to what you actually have for the DSP full carrier. The only difference is that the eta that you actually have is different, and the expression for eta would actually be given on your formula sheet. Any further questions? It's 9 minutes to 10 now.
I do have a few more questions, if that's okay.
Go ahead.
In the previous question that we looked at with the triangular signal, if we had to work with the autocorrelation factor, so if it was just a sinc squared function, would the bandwidth then be, because the sinc squared, like, it has multiple separate like little pieces to it that kind of continue infinitely. So then would we just consider the first intersection as the bandwidth?
Oh, wait a minute. Okay. Let's not get confused between time and frequency. Right. So
sorry, as if the sinc squared function was the frequency function that we were working with.
Okay. Now, so it means, in fact, what you're saying is, what would happen if the autocorrelation was triangular? Okay? If the autocorrelation was triangular, like this, okay? So this will be, let's say, R of tau. Because in this case, it's actually given in reverse. The sinc function is in the time domain, and the triangular function is in the frequency domain. So what you are saying is, what if the question had said the autocorrelation is triangular? Then in this case, what you would actually find is that the inverse Fourier transform of that would now be a sinc squared function. And your sinc squared function would have something that does this. That will be what will be the power spectral density of a signal. A signal that actually looks like this in the time domain will have a frequency domain that actually looks like that. Okay, so let's make this 1, and let's make this essentially -1. And don't forget that this here now is actually in time, so this is tau, and then this here would be frequency in this case. Okay, and then this also would be 1, and this would be equal to 2, and etc., etc. Now, your signal in this case now has essentially an infinite bandwidth, right? Because sinc squared goes to infinity. But in a real system, you would not use a bandwidth which is infinity. So you would truncate this frequency response at some point, depending on how much distortion you want in the signal. So let's say you decide that you are going to truncate it here, and you truncate it here, which means essentially you are excluding those components there, and you are excluding all the components on this side. then this here would then define what your bandwidth would be. Well, this is negative frequency, and then so this essentially would define what your bandwidth is. Am I getting your question?
Yeah. So then, is there a convention as to how many of the like side loops to consider, or is that completely up to the person implementing it?
It depends on the amount of because by truncating it in frequency to a certain point, you are actually distorting the signal. If I take this truncated signal, okay, I remove that. I take this truncated signal and then I do an inverse Fourier transform. What you will find, and is in this case, let me get another pen, blue. What you will find is that in the time domain, you will have something that has got ripples here. And then it will do that. And then out here, it will have some ripples as well. And then it will do this, and it will have some ripples here before it settles down. Okay. So essentially, by truncating it in the frequency domain, you are actually taking it into a filter, and the filter eliminates parts of the frequencies. And in the time domain, you'll be constructing a signal that actually is not the same original ara of tau, but it's a slightly different ara of tau. So the question simply, in terms of actually truncating, if you use an infinite bandwidth, then you will have a perfect triangular waveform. If you restrict the bandwidth somewhat, then what you're going to have is you're actually going to have this distortion, and that sort of distortion is then a matter of actually how much distortion you are prepared to tolerate.
Okay, that makes a lot of sense. Thank you.
Okay, yeah.
Yeah,
and in fact, in a normal transmitter, that's essentially what you do. Because if you look at, let's say we take a music and they are sort of playing music. Now, although the radio station works with a bandwidth of actually 15 kilohertz as the base bandwidth, but with music, depending actually on what music you're playing, you might actually have frequencies that go beyond 15 kilohertz. If you have some soprano or some lead guitar, that some acoustic guitar that actually is at fairly high frequency, what you might actually find is that the frequency response of the signal that you're transmitting goes beyond 15, but what you simply do is you truncate it at 15, and you say, this is the bandwidth that I have, this is the bandwidth that I'm working with for the baseband signal. Okay. And so, but by truncating it, what it means is that you are essentially introducing a little bit of distortion in your music.
Okay, great, thank you. And then just a question on the lab. For question 3, for plotting of the spectrums, is it required to plot a phase spectrum in addition to the amplitude spectrum, or is it kind of redundant?
Let me remind myself by actually going into, let me pull out the, I have time. I hope you guys have time. If anyone is rushing for time, it's fine. You can leave. Let me find it in my file. Damn, I must start organizing my files a little bit better than this. It's lab 2. Okay, right here, I've got it. Okay, right. Can you see my screen?
Yes.
Okay. So which part are you referring to?
Question 3 for the plotting of the spectra.
Okay. didn't notice that. Now you can actually do just simply the amplitude spectra, that's fine.
Great, thank you. And then just another comment on the actual limits.
Sorry, on the one of you sent me an email about what you can use from MATLAB. Essentially, you can use any object from MATLAB. So if you want to do an integral, you can use MATLAB has lots and lots of objects for doing an integral. And if you want to plot this signal, you can essentially plot it by actually using the MATLAB FM modulator object, or you can essentially calculate this actual phase. You can calculate this phase term here. Well, sorry, it's this second term here. You can calculate the phase term and then embed it in this and then simply plot that. So whichever way you actually do it, it's really up to you. Okay, and your other question was?
Just with regards to the limits placed on M of t, there's a double definition of the one limit. I just wanted to check. So at the in the actual definition of the baseband message, the 0.1 is defined for both the 10 and so for two instances, it's included.
Yes, so essentially, if I were to actually draw this, essentially your M of t at t equal to 0, obviously for t negative is 0, M of t is 0. So essentially, if we look at it for t equal to 0, your M of t is 0. And then between 0 and 1, it's a linear function. And at t equal to 0.1, M of t would be equal to 1, right? We're going to be 10 times 0.1, which is equal to 1. Correct? And then,
yes.
okay, right. And then after that, you now move on to the second segment. And the second segment starts at t equal to 0.1. Now at t equal to 0.1, using this here, it means it will be 2 minus 1, which is 1, which is exactly the same value that you get from that. Right? And then it decreases. Making sense?
Yeah, so the reason that I'm asking,
at t equal to 0.1, using this here, the value of M of t will be 2 minus 10 times 0.1, which is equal to 1. And using the first segment at t equal to 0.1, then M of t is actually equal to 1. So the two limits are exactly the same. They give you the same value.
So the reason that I was asking is because in MATLAB, it gives like a weird line that continues going up when I include both of the limits. So would it be fine if I just included one of the limit, like one of the equals on one of them?
Yes, that will you can use either the first one, and then let's say you were using you were evaluating it in steps of, let's say, 0.01, right? So you would find the values of your t. Let's say they are changing by 0.01. So you would essentially go from 0 to 0.1, and then for the second segment, you start it at 0.11. Am I making sense?
Yes, thank you.
Mm-hmm.
And then I just had a few questions about the upcoming test.
Right.
More specifically, like what the scope is and what the format will be.
Okay, right. So the test is going to be on the 17th of September. That is the date that the class reps have given me, which is next week on Thursday. And the time would be 10:15. It actually starts at 10:15. And it will go from 10:15 to 11:30. Essentially, it's an MCQ test which should take you no more than 30 minutes. So if we were doing this on campus, essentially you would be allocated just simply 30 minutes to do the MCQ. Okay? But because of the offline issue, it will be essentially, I've added another 45 minutes to it. So you will have from 10:15 to 11:30. And you would do it directly on Sakai. Have you guys done any of the MCQs on Sakai?
Yes, sir, we have.
We have, but each of the different subjects has had a different implementation of how they do an MCQ. So in subjects, it's just been a matter of choosing the correct answer. In other subjects, it's been a matter of justifying.
No, in this case, it's a matter of just simply choosing the correct answer. It's a standard MCQ with a question and 5 possible answers, and you tick one.
And there's no negative marking implemented.
There is no negative marking, but you need to actually have a crib sheet on the side where you can essentially do your working, because essentially let's take the previous question that we had, okay, where we calculated the received power. The question might be like that, and then it will say, what is the received power? A, 2 kilowatts, 1.5 kilowatts, 7 kilowatts, to 4 kilowatts, none of the above. Okay, so essentially you have to calculate it on the side so that you can then see which of the answers are actually correct. But I don't need your crib sheet. I don't need you to submit the crib sheet. All I'm simply looking at is whether you've ticked the correct answer or not.
And then it's a synchronous test. Everybody has to start at 10:15. Like there's only one access time.
Yes, everyone starts at 10:15 and finishes at 11:30. If you are a little late and you start at 10:30, that's still fine. You can start at 10:30 as long as you need to finish at 11:30.
Okay, great. And then just a question on the scope. Is it everything that we've done up until next week, or would it be everything in the third block, or like?
It's everything that we've done up to this week.
Okay,
so
great.
Yeah. It's not good. Yeah. So everything that we've actually done, it's essentially everything on linear modulation. The next bit that we're going to start next week is on digital modulation. So it's everything on linear modulation. And then the second MCQ, which you guys said you want to actually have, you gave me a date in October. It's going to be on digital modulation. Now, I actually urge you guys to ensure that you do your labs properly, because that's actually a very easy way of scoring good marks. And also pay attention to the MCQ, because it's also another way of actually scoring marks. The exam, there's still some discussion on the exact format of the exam. The exam would be a little bit more complicated. The test is simply there to show you what to study and what to look at. So it's not really a difficult test. If you look through the tutorials and you look through the notes, you should be perfectly fine. In fact, if you go through the tutorials and you understand all the tutorials, you should be perfectly fine in the test. Anything else?
Sorry, sir, just on a follow-up on Tali's question. So it's just basically tutorial 1 and tutorial 2 that we have to do for the
Yes.
test. Okay, thank you.
Yes. No, how many tutorials have we done so far?
We've done 2. I think that we're meant to be starting the noise tutorial tomorrow, so I'm not sure if that would also be then included.
Didn't we start on the noise tutorial last time?
Because the week that the noise tutorial was meant to be started in was quite intense, you said that we weren't going to start it.
Okay, yeah, but we will finish the noise tutorial tomorrow. I'll just make sure that I don't put a lot of noise, complicated noise stuff in the test. The test will be fine. You should be fine. But what is important is you might want to, because there's a formula sheet, so that you are not toggling from one screen to the other. If I were you, I would make sure that I actually download the formula sheet and I print it so that it's on my, I have it on print. And then I have a crib sheet where I can actually work out the answers before I actually choose the answer on the MCQ. And bear in mind that you are not going to be rushed for time. You're going to have plenty of time. Okay. So we meet tomorrow at the usual 10:15 tomorrow?
Yes, sir.
Okay.
Sorry,
Now,
can I ask one more question?
Yes.
How much annotation would you like in the lab explaining what we've done and why?
Okay, let's can you still see my screen?
Yes.
Oh, okay, right. Let's take, for instance, the first part. Plot the message signal and its integral on two separate graphs. Okay, so essentially what I'm expecting you is to answer the questions directly. So you actually plot the signal. So if I were you, I would essentially say m of t is equal to blah, 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 which is essentially copy that expression for m of t, and then you give underneath a graph for m of t, a plot for m of t. And then underneath you give a plot of the integral of m of t, and that's it. So I'm not expecting you to actually then discuss the results, comment on the results. No, you simply answer the specific questions that have been asked. The second part then says plot u of t. So essentially you give the plot of u of t. Now, some of you said that you actually want to do using what you call it, this MATLAB thing, where essentially you will have a bit of code and then you have the graph below it. That's fine with me.
Okay, thank you. That clarifies it.
Are you okay, guys, with the first lab? I had, I would say, over 30 emails from individuals asking about various things. But as far as this lab is concerned, I think I've only had about 2 or 3 email queries. It either means you haven't yet started looking at it or you are perfectly fine. I'm not sure which is which. But I'm quite happy to actually get questions by email. Okay, right. So we will have a chat on tomorrow when we look at the tutorials. But I'm concerned about the attendance. I mean, at the moment there are 9 of